Chapter 5, Eigenvalues and Eigenvectors. Now, if there is ever an impressive sounding topic, it is the topic of eigenvalues and eigenvectors. In fact, this is so popular that I think one of the recent Marvel movies, Avengers movies, used eigenvectors in their fancy time machine thing. I haven't seen these movies, so I don't know what it is, but I do know that at one point someone says, we're going to find the eigenvectors of the Mobius strip, which, by the way, is a little ridiculous because I don't know if eigenvectors of a Mobius strip even makes sense. I do know that I was actually teaching this chapter, 5.1, the semester that movie came out, and I think every student in my class came by and said, Dr. Fisher, they mentioned eigenvectors in the Avengers movie, and I was excited for them. Okay. Anyway, eigenvalues and eigenvectors. These are impressive sounding words, but the concept is actually not that hard. So whenever you talk to your parents or someone else in your house, make sure you say, I'm studying eigenvalues and eigenvectors, so they sound like you're really doing something amazing. But the concept is not that complicated, but it's one that a lot of people, even though these vectors are used throughout science, throughout engineering, they're used lots and lots of places, a lot of people don't really understand this very simple concept of how we think about it. At the premise of eigenvalues and eigenvectors is this. It's that we're mapping vectors from one space to another space, and every vector that you map gets mapped to a new vector over here. And our real question is, what happens to all of the vectors? And it turns out some of the vectors are more important than the others, because there's some vectors that create kind of a basis for how we think about everything that's happening in this map between these two spaces. And those are the eigenvalues and eigenvectors. This is closely connected to the idea of a steady state vector from the last section, from the problem on Markov chains. Okay, so let's start with this problem where we map two vectors under a matrix and see where they go. So we have our transformation matrix is the matrix 2, -1, 1, 4, and we're just going to map two vectors. So let's look at the vector 2, 1 and see what happens when we map it. And so mapping is just multiplying, right? Mapping is just taking this and multiplying by that. So we get row times column. That's 4 minus 1. Looks like I get 3. And then row times column is 2 plus 4, and we get 6. So 3, 6 is the vector that shows up there. And now then the next one we're going to do is 2, -1, 1, 4, and we'll have 1, -1. And so now we're going to do row times column is 2 minus 2 plus 1 is 3. And here we'll do 1 minus 4 is -3. And it turns out one of these vectors is an eigenvector. And let's look at the map and see if we can kind of see what's going on. So here are my two vectors. I attempted to draw them. So this is the vector 2, 1 right here. And this is the vector 1, -1 right here. So let's map our answers on here. So my first answer is that this one, 3, 6, or 2, 1, goes to the vector 3, 6. So let's just put it on here again. So this went to 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3. So that one mapped to that vector. Okay. But let's compare that to this one, which went to the vector 1, 2, 3, 1, 2, 3. So that one goes to this vector. What we're going to find is this vector is important because it doesn't matter how many times you map it, this vector will always continue to be pointing in the same direction. Versus this vector, as you keep mapping it, it'll keep pointing in different directions and doing different things every single time. So this one, we're going to say is an eigenvector. This one, we're going to say is not an eigenvector. So just a really quick summary of what an eigenvector is. An eigenvector is just a vector that when you map it, it gets mapped to 8 points in the same direction as it was originally. Sorry about that. So an eigenvector points in the same direction after the linear transformation. So let's think of what does that mean? That means that if you take your A and multiply it by x, what does it mean to be pointing in the same direction? Well, it means you actually have the same vector back again, except times some sort of constant. And actually, the traditional letter is the Greek letter lambda. So that's generally what we use for this constant. So notice that when I look at this vector 1, 1, after I map it, it's now pointing in the same direction. So it's the same vector, it's just 3 times the vector that it was. Okay, so that's an eigenvector, and this right here is what we call the eigenvalue. The eigenvalue is how much that vector has been scaled. Is how much the magnitude has changed in the trend. I didn't think about this before I started writing. In the transformation. These eigenvalues can be negative, so they don't have to point in the positive direction. They can be negative directions, and we'll see it's even reasonable to talk about complex eigenvalues, where these are complex numbers. That'll be one of the last things we do this semester, and I think that'll be pretty interesting. Okay, so eigenvector points in the same direction, and eigenvalue doesn't. So if I pull up this problem I had earlier, I would say that 1, 1 is an eigenvector. 1, negative 1 is an eigenvector. And it has an eigenvalue and let's go ahead and introduce that lambda, its eigenvalue is 3 because the vector became 3 times as large. What you'll notice though is if you took any multiple of 1, 1, if you did 2, negative 2, it would get mapped to 6, negative 6. So any combination of the eigenvector is also an eigenvector, and it has the same eigenvalue. Okay, so what we're going to do today is we're just going to kind of examine, if I were to give you some values and give you some vectors, could you determine are they eigenvectors or are they not? And then what we'll do in the next video is we'll come and ask this more important question. That is, if you just have any old matrix, can you then turn that matrix, figure out the eigenvalues and eigenvectors for a matrix? So why are these eigenvalues and eigenvectors important? They play kind of an important role in the field, in all sorts of fields, because these are the things that stay the same. These are the things that are constant. And just like in the steady state vector, because those vectors stayed the same from one map to the next, you knew that in the long run, other things would kind of gravitate towards those steady state vectors. And so eigenvalues and eigenvectors have some of the same long run properties about the transformation. They tell you in the long run, what are all vectors tending towards, and then similarly, are those vectors tending to get bigger or smaller? So it gives you some sort of picture of what's happening in the long run for transformation, if that transformation is repeated over and over and over again. And that's often how we want to think about things. Okay, so what we want to do, exercise 5.2, is we want to show that 3, 1 is an eigenvector of 1, 3, negative 1, negative 1. And how do we do this? By the way, this is a great time for you to pause, try this problem. My guess is that you can knock this out of the park based on what we just did a second ago. Okay, so now that you've paused and you've tried the problem, how do you show that it's an eigenvector? Well, what you do is you just multiply. 1, 3, 1, negative 1, and we multiply by 3, 1. And when we multiply, what do we get? Row 1 times column 1 is 3, plus 3 is 6. And 1 times 3 is 3, minus 1 is 2. And so we get 6, negative 2. What do you notice? 6, negative 2 is this number times 2. So we just multiplied that vector times 2. So this is an eigenvector, and the eigenvalue is simply the eigenvalue of 2. Okay, the second problem is going to be a little bit more complicated. So let's move to exercise 5.3, where life becomes a little bit more interesting. So exercise 5.3, we want to show that lambda equal to 3 is an eigenvalue of that matrix that we've given. Well, what that means is that if you take that matrix and multiply it by your vector, what should we get for the answer? We should get 3 times that vector out. Okay, if this feels a little bit like what we did with the steady states, that's good. That means that you're making connections. Because what we're going to do here is we're just going to do some algebra on this problem. So I'm going to start by subtracting this over to this side. And we'll have ax minus 3x is equal to 0. And this is, we need to think of this as a 0 vector. Okay, now what I'm going to do is I'm going to factor the x out. And so we'll get a minus 3 times x equals a 0 vector. But it doesn't make sense to subtract a constant from a matrix. These are not the same type of objects. But what you can think of this 3 is it's like 3 times the identity matrix being multiplied by that vector. And that makes complete sense to us. So now what I want to do is I just need to solve this homogeneous equation. So notice that for us, since A was, since A was 2, 1, 1, 2, then we're subtracting off the vector, the matrix 3, 0, 0, 3, and this is times x equals 0. And so this is one that we can now start doing really, really quickly. And so this is 2 minus 3 is negative 1, 1 minus 0 is 1, 1 minus 0 is 1, 2 minus that is negative 1. And so that x equals 0. And so we have negative 1, 1. If I want, I could put my zeros over here, and this is the problem that we're solving. My guess is that you all can do this very quickly. You just notice you add them together, and we get negative 1, 1, 0, 0, and then we've got zeros on this side. So what's our solution? Our solution is that negative x plus y equals 0, or x equals negative y. And y is free. So that means that I now can write down my answer in a nice vector form. And so my vector form is that xy is equal to, well, x is equal to negative y, and y is equal to itself. So it's that times y. So negative 1, 1 is our eigenvector. So negative 1, 1, or any multiple, right? So negative 2, 2 is also an eigenvector. Negative 3, 3 is also an eigenvector. So this is our eigenvector. Maybe we should go up and test it and see if it works. So let me just grab a different whiteboard. And I'm throwing things around the room. So let's just use this whiteboard, and let's just check our answer just for fun. So if we check our answer, what am I going to do? I'm going to take 2, 1, 1, 2, and multiply it by the vector that we just got, which was negative 1, 1, and see what we get. And if all works out correctly, we'll end up with the same vector but multiplied by 3, because this had a eigenvalue of 3. So there's negative 2 plus 1 is, oh, hold on a second. Let's see. Did I get that right? Hold on. I think I messed up my answer, didn't I? So, okay. Let's do that again. Sorry, folks. This is not professional. I'm not a professional. I'm a math professor who teaches in classrooms, not on YouTube, but today I am. So our problem, we had x minus y equals 0. It should have been, or negative x plus y, it should have been x equals y. That's what it should have been. So our vector should have been this, xy equals 1, 1 times y. So our eigenvector should have been positive 1, 1. Hopefully I didn't throw you off too much there. All I did was I got a negative sign wrong when I moved this to the other side. So I moved it to, solved it, and lost my negative sign. So hopefully you saw that and you were screaming at me a second ago. Maybe not screaming so loud that it was awkward for your family. But okay, but this should be a positive 1, 1. And now let's look at it and see what we get. Row times column is 3. Row times column is 3. And so notice this is a eigenvector and it has an eigenvalue of 3. So it checks out exactly as we expected. Okay, let's flip over to exercise 5.4 and let's hope that you all can start making sense of this one. So you should pause the problem and try it. This one's harder because it's a 3 by 3 matrix, but the principles all remain exactly the same as what we did a moment ago. Okay, so try 5.4 and see what we get. Okay, let's go for it. So now for part A, all I'm going to do is I'm just going to do some multiplication. -1, -1, 2, 3, -5, 6, and -1, 1, -4. And I'm just going to multiply that by the matrix I'm given, 4, -1, 1, and see what I get for my answer. And if this is an eigenvector, then I'll get some multiple of this number out. So let's see, so row times column, -4, -3, -1, and I get -8. -4 plus 5 plus 1, so that's -4 plus 5 is 1, plus 1 is 2. And here I've got +8 minus 6 is 2, minus 4 is -2. And did that work out? The answer is yes. This vector is a multiple of that vector, and its eigenvalue is -2. So this is an eigenvalue vector. Its eigenvalue is -2. Okay, so that's good. So 5.4a works out really well. And I guess this is part B. The corresponding eigenvalue is that number. Now, can we find a basis for all vectors with an eigenvalue of -2? So are there other vectors that have an eigenvalue of -2? The answer, I hope, is yes. And the way we're going to do this is the same way that we did earlier. And that is we're going to do that algebra where we do ax equals, and this time it's -2 times x, because if this is an eigenvector, then that means when you multiply it by a, we get that same eigenvector across here. So let's do this algebra. Ax, it's the same algebra we had a second ago, except we have a different number on this side. Plus 2i times x equals 0, and these are the 0 vectors. So let me now replace this with the actual matrix that we have. Okay, so there's our matrix, and now let's start simplifying this thing. So we just subtract across, and it looks like the matrix that we're going to have is going to be -1 minus 2, so -3. 3 minus 0 is 3, -1. Our next column is -1, -5 minus 2, so that looks like a -7. And then 1 minus 0 is 1. Let's see, am I doing this right? Okay, I think I haven't messed up yet. So it's always a yet, isn't it? And then my next one is 2 minus 0 is 2, 6 minus 0 is 6, and then 4 minus 2 is a -6. So I think these are my numbers. Let me hold on it. I just want to make sure that I haven't messed up yet. So that should be a -3, and then those should be the same. Those should be the same, and that should be a -7. Good. Did I get a sign wrong there? Oh, that's my problem. I'm adding these things. These numbers just felt wrong to me. Okay, good. Again, you caught me. Hopefully you yelled out, Dr. Fisher. I heard you yelling. That's what changed it. Okay, so -1 plus 2, that's a positive 1. Good. -5 plus 2, that's a -3. And -4 plus 2, that's a -2. Okay, this is great. And so now I'll just take this and I'll just put my zeros over here so I can row reduce and see what happens when that equals 0. This row reduction, you could do it in your calculator if you want, but I want you to notice this is going to be really easy because this first column is going to stay the same. But when I add this plus this, I get 0, 0, and 0. So that second column, that second row becomes all zeros. Furthermore, when I double this, I get the exact same thing. So this one all becomes zeros. So what we ended up with when we did this problem was we ended up with 2 free variables. We ended up with 1 pivot and 2 free variables. Both y and z are free. So when I come over and start writing this out as a solution, what am I going to get? I'm going to have x plus 3y minus z equals 0. Or if I like, x equals -3y plus z. And that means that my solution is now going to have 3 parts in it. We're going to have an x, y, and z, and we're going to have 2 vectors because we have 2 free variables. We'll have the y vector and the z vector. And so they're both free variables. So x is -3y's and 1z, and y is equal to y, and it's not equal to z, and z is not equal to y, and it is equal to z. So what does this mean? This means that all of our eigenvectors are of the form are made up with the basis of these two. So remember what basis means? Basis just means that it's the combination of every eigenvector can be made by some combination of those 2 vectors. And so combine these 2 vectors in any way you want, and you get a basis for, and you get an eigenvector. And hopefully this makes some sense. By the way, using terminology from earlier in the semester, what we did was we found a basis for the null space of this kind of modified matrix after we'd subtracted or added the 2i to our matrix. So this is our basis. Now what about that problem that we had earlier? So earlier we had that 4, 1. Earlier we had that 4, -1, 1 was an eigenvector with lambda equal -2. Well, how did this come from here? Well, the answer is if we took -1 of these, -3, 1, 0, plus 1 of these, 1, 0, 1, we get our 4, -1, and 1. So the answer is this vector is made up of -1 of these and 1 of these. So this vector is in our basis. So this is an example of one of our eigenvectors. It turns out we get many, many eigenvectors. So I can ask you at this point, can you tell me another eigenvector? And the answer is, yeah, any combination of these 2 are eigenvectors. So another eigenvector. So another eigenvector might be what happens when we just add those together. So what happens when we do -3, 1, 0 and add it to 1, 0, 1? And the answer is -2, 1, 1. So you could check that, and this would be another eigenvector with lambda equal to -2. Knowing you all would pick like 17 of these and 25 of those or something. So go do that on your own. Enjoy that. I'm not going to do that here for you. But the collection of all eigenvectors, so all eigenvectors, I'm struggling with my spelling. All eigenvectors with the same eigenvalue create what we call the eigenspace. And so notice these eigenvectors would be the eigenspace for lambda equal to -2. So this is the eigenspace connected with that eigenvalue. So that means that everything made up of those 2 vectors are those. And there's a nice little result that says that as long as these 2 vectors are independent, then your eigenspace is actually, I think the eigenspace is all of your eigenvectors, period. And as long as all of your eigenvectors, you have the right number of eigenvectors, your eigenspace always makes orthogonal independent vectors. Not orthogonal, but always makes independent vectors. Sorry for the gibberish there at the end. So the takeaway from this section, what I really hope you can do is I hope that you're capable of calculating eigenvalues and eigenvectors. I hope that if I give you an eigenvector, you can prove that it's an eigenvector and find an eigenvalue. And similarly, if I give you an eigenvalue, you can go find the eigenvectors that come with it. Next time, we're going to ask the important question, and that is, where did these come from? How did I know these were? Did I just search for vectors until I found one that worked? Did I search for eigenvalues until I found one that worked? The answer is no. Given any matrix, we can figure out what the vectors are and what the values are. And that's a really nice result. And we will tackle that next time in linear algebra.